So modeling inversion 101 kind of applied to magnetic gravity and airborne electromagnetic data. And really just my motivation for this is pretty soon we're going to see these awesome examples, and there will be some probably modeling examples of the data. So I just wanted to give a quick background. This is by no means extensive discussion. So just why do we want to model our data? What are we doing? Well, really geophysics, to step back one, we're going for distribution of physical properties. And really, as Adam mentioned, we're all going to mention probably throughout the day, you need that physical property contrast for geophysics to work. But if you're fortunate enough to have it, then modeling inversion are often a good path forward. It's nice that you do quantitative analysis, maybe as opposed to looking at, you see a lot of great data today, maybe you can get, as Adam mentioned in this talk, you can get, depending on your data type, some depth information fairly well out of your data. So that's quite useful. It lets you look at your data in more ways. Maybe look at a map view, and that's also looking at map view, you can look at depth slices. I'll show you an example of that later. Cross sections or 3D views just gives you a little more options. You can identify targets or bodies. You can draw circles in 3D around them or 2D. And then often if you have something like a physical property model, maybe you'll combine that with another 3D model you have from other geoscience data. Maybe you already have some drill hole data, or you need some sort of basin line model of what you think the geology is doing, so you can compare the two. So you're going to hear this. Some people, you've probably heard it from geophysicists you work with, or geologists, people that do mining. There's something called forward modeling. And basically the concept of forward modeling is you create data from a user-constructed model. So you drew this imaginary geologic feature, and then it shows you what the geophysical data should look like from that feature. So I just drew a couple really simple models. I just drew this ellipse, the blue ellipse there, and it makes this bump in the data. And, Adam had shown basically real responses. Here, I showed some forward models where you have those different conductive features that are making different waveforms in the data. And then there's just a dipping model there. You could have any sort of model, and then you get some sort of data back from that. Now we're going to step the other direction through a process of inversion. Basically, we create a model from the data now through this process called inversion. And this is an iterative process. There's all different types of inversions. And I'm going to say this a couple times, and the other geophysicists will say this too. You've got to be careful, Ken will warn you, everyone will warn you. The results are non-unique. So you can have any number of sort of geological models you come up with that can fit the data. There are things you can do to prove your confidence in your model, and they are definitely help. And basically what you have there, you have your observed data as a solid line from this model, this ellipse down there. And then the inversion process went forward, and it made a model, and it created, the model generated data as an orange dashed line. So at that point, you say, okay, my model fit the data, in quotes, and that means the data that the model produced was pretty close to observed data. So let's see how this might pan out in this very simple case here. Like I said, it could be an iterative process, so you just start with, you have this ellipse you drew, and it's down there, and then the predicted data really doesn't fit the observed data. This is the first step in the iteration. The computer program is going forward, and maybe it's too shallow, not big enough. Then the computer program marches through and adjusts the model. It says, okay, now we're getting a little closer. Maybe a little bigger geologic blob down there. And so the curves look a little better, but the location's not great. We'll just keep marching forward. It's going through, and it depends on software. It can take weeks, days, a few minutes, depending on what you're doing. And it might be a few iterations, it could be 100. It just really depends on what you're using. And now we go. We march through, and now the software says, it's done, my data fits pretty close, and this is what we got back this model. So now let's talk about, this happens to be something called a parametric model, is what I showed. So there's more than these, but these are some basic model types and inversion program types that you'll hear geophysicists talk about or you'll see results from. So the first one, the upper thing, is something called a parametric model or inversion. So in this case, you're solving for a specific body. It might have a certain depth, shape, size, or dip, and then you assign a physical property to that. So it's kind of like the simplest type of modeling. It's really common for gravity and magnetic data. People do this all the time. You can do it by hand, or you can run a program, and you can get some pretty informative results from it. Then there's another type of model called a layered Earth model. So that's the middle one there, where you just have a fixed boundary, and then each zone in there that's a different color has a fixed physical property. And so in this case, if you're forward modeling, you would draw out what you think you have in the subsurface, your geologic model, and look at the data that you think would come back from it. Or if you're running inversion, you might either say, you might draw the shape and you solve for physical property, or you can solve for both the boundaries and the physical properties of each layer, or just the layer boundary location. It just depends on what you want to do. And there's a third type of model that's often very common in use. It's called either smooth or discretized. And essentially, you're just dividing your modeling space up into little cells. It could be either just as you go down depth in a 1D sense, or in this case, I'm trying to do a 2D model, you just have this cross-section of little cells. Or in 3D, you can imagine cubes, and you can, sometimes they're rectangular, they can be any shape, there's lots of fancy things that come. Now let's step back a little, because now you're going to also hear the terms 1D, 2D, 3D, we throw these terms around all the time. And so in terms of a model or inversion, when we talk about 1D, we usually have depth in the sort of exploration sense. We have depth in a model value. So this is a super common type of inversion for EM data. It's probably the most common for airborne data, this type of modeling inversion. And I'll just go, so I drew two figures, pretty simple, ways you might represent this 1D model. You might just kind of have a stack of cubes and color to the model value. Or another thing, you might see a plot of a model. So in that case, the figure on the right there, the vertical axis would be depth, and then the horizontal axis would just be model value. So maybe it's resistivity with depth. Okay, now we're going to switch to 2D. So, and I'll mention one thing that's kind of aside because you'll hear it, but a lot of times when you do these 1D models, you might, if you're running an inversion, you might have them look at their neighbors so they come out more similar to their neighbors, and that's a way of controlling the end result and to give you more confidence in each individual model. So now we switch to 2D. It's like, all geologists think of it as cross-section. And in terms of the modeling inversion sense, you're either assigning a depth and a distance and a model value, or solving for both those. So you have more to solve for. It's computationally more expensive than a 1D model. And these are pretty common for magnetic and gravity data, and they're out there for electromagnetic data. It's definitely less common to solve for 2D. I think for the airborne electromagnetic data, but it's out there. You also have to think about, so there's 1D, 2D, and 3D inversions, but when you look at the model someone presented you, it may be a 2D cross-section, but that is probably it could be the combination of 1D models. So that's sort of the source of where it came from, but you're seeing information in 2D. And then we move to the lowest example there, and it's like the full 3D model. You're modeling your whole space in 3D. So in that case, you get X, Y, Z location and a model value. And these inversions and models can be generated for magnetic gravity and airborne electromagnetic data. Especially for the electromagnetic data, it's really computationally expensive, which means it takes a long time to get results. And it's much more difficult to create the programs that would do this modeling inversion rate. It's certainly not everyday practice for airborne electromagnetic data. By far, most common is the 1D model. And you can imagine that these results you see, and I'll show a few examples, can be the result of either combining your 1D models or your 2D ones. So I forgot to mention one other thing. It's also common when you look at a 2D model, it might just be a cross-section removed from a 3D space. Okay, so just a little bit of talk on, since we're going to see a lot of results on the electromagnetic data today, what happens when you do an inversion, you generate, what do you do with electromagnetic data? You get either a resistivity model or conductivity model back, because that's the physical property that the technique is sensitive to. It's pretty common to see results, and I'll be showing some, from either a smooth or a discretized model, like I showed you. But that's not to say there aren't layered models out there. Adam actually already showed an example of a layered inversion. And sometimes you'll hear something called a plate model, which is often used to model a conductive target. And people still do this. I actually wrote some of the popular software out there. And that would be an example of a parametric model for EM data. And Adam alluded to this before, and he talked about his presentation. What's really important here is that the EM method gets information at a single point from multiple depths by virtue of the different frequencies that you're collecting, or if you have full or if you're recording time data, you get data coming back at different times. So because of the wealth of information you're collecting, you're able to get pretty good depth information back from your inversion models. Now I'm just going to show some examples. This is actually an output from a pre-computed program. It's UBC's EM1DFM code. We're going to focus in on the middle plot there. And so that horizontal axis there is depth increasing to the right, and then the vertical axis happens to be conductivity, which we discussed is the same as resistivity. And it's a lot. Geophysicists tend to put things in all different units and ways to visualize it. But the key here to note is that that physical property is changing with depth. And another thing you'll notice that near the surface, each little step is a lot closer together than as you get further in depth and further apart. And that's the fact that the method has more ability, more resolution near the surface than it does at greater depths, and that's true in all geophysics methods. And the bottom figure there just happens to be this program is also solving for the magnetic susceptibility. So that's a 1D model. Okay, and then I just took the middle one right there. We're going to switch to a 2D model, which I'm showing. For reference, in the upper right-hand corner, that's the same conductivity model. Now, that model value is on the horizontal axis, and as you go down in depth, that's going to be up. And then the main figure you see is a 2D model from combining 1D inversions. So in this case, this is actually an example of electromagnetic data. So the horizontal axis is distance, and the vertical axis is elevation. So it basically makes a cross-section. And then the model value, in this case, the colors represent the different resistivities. And later on, I'll be showing you examples of these. And now, okay, now we have a 3D model. This is just a 3D view. All those one-dimensional inversion results, resistivity models, stitched together and gridded by a program called ProCAD in this case. And you can see now there's 3D volume of resistivity values that I can go ahead and interpret for whatever I'm looking for, whether it be permafrost or hydrology boundaries or mineral deposit. That just gives you a sense of the difference between. And then I'm not sure if there'll be any magnetic and gravity examples I didn't look through, but basically you can do the same thing for magnetic and gravity data. So in this case, you're looking to get back density or magnetic susceptibility, or in some cases a magnetic vector. The depth information can be more difficult to obtain than the electromagnetic data, and that's by virtue is that instead of that single point having some depth information, you actually need the whole profile in your surrounding area, or the map view, basically the survey footprint. It determines the depth of information and exploration, and also determines that you need that distance, and that signal over that area is what tells you how deep something is, not the single data point. So and then also, it's pretty common to see parametric inversions layered in smooth types.
2 minutes, April?
2 minutes. Good. 2 minutes for the buyer beware message. So like I said before, in all of us, you need a physical property contrast. So don't bother modeling and inverting. You don't have that. And I warned again, it's non-unique. So that means you can have multiple types of geology and multiple models fit the data. So it's a good idea if you can get multiple models from multiple sources. What do I mean by that? It can mean two things. It could be using different vendors' software on the same data type and comparing those results and seeing where they agree. Or it could mean adding complementary information. In other words of warning, you've got to be careful of your depth of investigation. Adam was discussing that a little. That is, when he says the system can only see 50 to 100 meters, then don't go looking at your model below that, because it's not reliable information. Certainly on, this is kind of outside the scope, but on magnetic modeling, remnant magnetization, you have to be extremely careful of. That can really cause headaches in the modeling process. And that's where we go through constraint modeling or complementary geophysics. For example, I have a project where my permafrost over bedrock, they both have high resistivity values. So the electromagnetic data has a poor time figuring out the difference between those two. But fill and bedrock have a great density contrast. So maybe gravity survey is a big complement to that. Okay. That's it for that.
Good.
I think we're on break, right?
We are.